There were 2, 3, 2, 1. Okay, there are a bunch of symmetries when you're talking about something that is in free fall. Let's pretend that you have an object that you toss up in the air and it goes up and comes back down. Okay, so there are a couple things that you can take advantage of, but only once you have shown them mathematically. You can't just say, I have a gut feeling that this ball probably goes up at some speed and that when it gets down, it probably, just because of the symmetry of the parabola, is the same. But let's prove that, because that happens to be true. That's why you don't throw things up in the air really fast and then stand under them waiting for them to bonk you. Okay, so remember, we can use the constant acceleration equations whenever we want, as long as there is constant acceleration. So I'm going to look at this thing. I'm going to look at this whole thing and use this equation. All right, and what do we know about delta y if we're talking about the ball coming back down to the same place? It is 0. Oh, that is awesome. So that means 0 equals vf squared minus vo squared. And so then I can say vf squared, vo squared, those are the same. Now you may notice that if you take the square root of both of those things, that you have to make sure that you keep in mind that VO really is negative VO is what VF is, right? Because one VO going up has a positive velocity, VF is down, but they are the same in magnitude. So I would say that anytime that you're talking about something going up and down, if it returns to that same height and it is accelerating at a constant rate due to gravity, or really anything, I guess, that we have this is one more tool in our tool belt. Okay, so when delta y is 0. Second thing, you may also think, hey, maybe there's a relationship between the time on the way up and the time on the way down of that object in free fall. And you might be right, but again, we got to check it before we wreck it. Okay, so let's look. It's much easier to take the trip down first, because all of the constant acceleration equations have VO in them. And what do we know about VO on the way down? It's 0. How come? Because it's at the tippy top of its path. And so its initial velocity is 0. Okay, and again, just to refresh our memory, we're talking about T up and T down. You don't have to make those noises. I do it for you, so you don't have to. You're welcome. Okay, so T on the way down and T on the way up, are they the same? All right, so let's look at T on the way down first. All right, so I'm going to do VO down, that's 0 meters per second. VF down, I don't know. Delta Y, I don't know. Acceleration, and T down. Okay, we know the acceleration is G, and we happen to know zoop, our T up stuff. VO on the way up, I don't know. VF on the way up, that's 0, right? Because when it's at the tippy top of its path, the velocity is 0. Delta Y on the way up, I don't know what it is, but I do know that delta Y on the way down is negative delta Y on the way up, right? Because the change in vertical velocity on the way up is the same in magnitude, just opposite in direction. Acceleration, G, time up. All right, so let's see if these chompy chomps are the same, okay? So I think looking at the equations that we have, that we don't really have a whole lot going on the left. So I think that really, because, as we said before, all of those equations have the initial velocity in them, I think it'd probably be best to solve for the initial velocity first, okay? We can say 2a delta y, this is on the way up, equals vf squared minus vo squared. And again, I'm going to just subscript these. I guess I did not need to subscript that. All right. What do we know about the final velocity on the way up? 0. Thank you. All right. So we got VO equals and is that a problem that there's a negative under the root? No, there is not, because that acceleration is also negative. Okay, so we have our initial velocity. It happens to be that somewhat gross looking thing. All right, next, let's use our equation to say VO up, or VF up equals VO up plus AT up. And what you'll notice here, oh, I love a good 0, gadoosh. And we end up with time on the way up is equal to negative VO up over the acceleration. So if we can show that time on the way down is equal to that same thing, then we are golden. So let's do it. We got that same old equation. Let's use that. Yeah, let's use that same exact one. Oh no. What was the equation I wanted to use? Vf equals VO plus AT. And this is VF down, VO down, and time down. All right. What do we know about VO in this case? 0. What do we know about VF? Well, let's put it in terms of stuff that we know. All right. What do we know about VO and VF? Well, remember from this thing before? All right, so that means that VO, if we're talking about the entire trip, is the same thing as negative VF, and vice versa. VF is the same thing as negative VO. So let's put that in here. We got negative VO, and this is up. And, oh, I think you're seeing where this is going. They're the same. Okay, so when the object is coming back to that same height, it takes just as much time to go up as comes down.